How does convolution work in Neurotech? Have you ever wondered how machines can interpret brain signals or images? One of the key techniques that makes this possible is convolution. Let's break it down in simple terms. Convolution is a mathematical operation that plays a vital role in signal processing, especially in neurotechnology. It is commonly used in neural network models, particularly convolutional neural networks, which are inspired by how our brains work. So, how does convolution actually function? Imagine you have a small matrix called a filter or kernel. This filter moves across your input data, which could be brain signals or images. As it slides over the data, it multiplies its values with the corresponding values from the input. Then, it sums these results to produce a single output value for each position. This process creates what is known as a feature map, highlighting specific characteristics of the input based on the filter's design. In the context of neurotechnology, convolution is essential for processing various neural signals, such as electroencephalography, functional magnetic resonance imaging, or intracranial recordings. These signals can be quite noisy and complex. Convolution helps to isolate important patterns related to brain activity by focusing on relevant spatial or temporal features while minimizing noise. Convolutional neural networks use this operation extensively. They mimic the visual processing system of the brain. Each neuron in these networks responds to a small region of the input, similar to how neurons in our visual cortex react to specific stimuli. This localized processing allows convolutional neural networks to learn features from raw neurodata efficiently without needing to manually identify them. Practically, convolution in neurotechnology enables several applications. For instance, in brain-computer interfaces, convolutional neural networks can decode neural signals to control external devices. They recognize patterns linked to intended movements or commands. In medical image analysis, such as with magnetic resonance imaging or computed tomography scans, convolution helps identify abnormalities or brain structures automatically. Additionally, it plays a role in classifying neural signals, like detecting epileptic seizures or different cognitive states by extracting features from brain recordings. One of the advantages of convolution is that it shares weights across different input regions. This reduces the number of parameters needed, making models more efficient and less likely to overfit. This efficiency is particularly important in neurotechnology, where data can be limited or costly to gather. In summary, convolution works in neurotechnology by applying localized filters to neural data, extracting meaningful features inspired by biological processes. It forms the foundation of many advanced signal processing methods and machine learning models that interpret complex brain signals for various applications.